And welcome back. So, function overriding and virtual functions. Some new terminology, uh, some new language constructs. We'll get into what this is, what function overriding is, and how virtual functions are useful in achieving that ends within this lesson. Before we begin, though, do not confuse function overloading with function overriding. They are different. So before we get into it, let's consider some cats and parrots as animals. So we can treat an object as an animal or as a cat or parrot, depending on our current view. Remember that when we're dealing with an object of a derived class, we have the ability to look at it through the lens of the base class or as whatever type of object it is. So we can look at an animal, so like a cat, or like the parrot Polly, through the derived lens. So as an actual cat or parrot object, depending on its type. In this case, the derived version is going to be used. So remember, when we asked Bubby to speak, he said meow when we were looking at him through the lens of the cat. So we can also look at an animal through the base lens. In the case of an actual, say, reference of animal type or pointer to an animal object where either the reference is bound to a derived type or the pointer points to the base address of a derived type. In this case, the base version will be used. So think about the implications of that. What do you think would happen if we were looking at Bubby as an animal or Polly the parrot as an animal through the lens of the base class, and we asked either Bubby or Polly to speak? What do you think would happen? Well, let's do just that. So we're going to initialize the cat Bubby, the parrot Polly, and we're going to take a reference. So Bubby, we'll look at Bubby as an animal by taking a reference of the base type and bind it to Bubby. And then we'll look at Polly as an animal through a pointer to an animal, and we'll initialize that pointer with the address to Polly. If we ask Bubby as an animal to speak or Polly as an animal to speak, we're going to see generic animal noise in both cases. And the question is why? Well, remember, we can look at an animal through the base lens. In that case, the base version is used. So in this case, the speak, because we're looking at Bubby and Polly as an animal, the version of speak that is being employed is going to be that of the animal. And in this case, the noise or the string that is produced upon asking that object to speak is going to be the generic animal noise as defined. Now let's, I don't know, maybe we're collecting, let's say we're creating some sort of program and we need to have a collection of animals. So we have cat, Bubby, and Polly the parrot, and a vector of pointers to animals. We could push back, say, the address to Bubby and the address to Polly to that vector. Now, at this point, each type within our vector animals is going to be a pointer to an animal object. In the case shown specifically on this slide, the addresses contained within that vector are addresses to derived objects, a cat and a parrot. However, because we're looking at those objects through the lens of the parent, and again, we're doing that with a pointer of the base class type initialized with the address of the derived class type. If we iterate through each element in our vector of animals, so for each animal and animals, and ask that animal to speak, well, the base class version is going to be used again. So we're going to see a generic animal noise. So the animal interface, and this is where we're going to start getting into function overriding, or at least some of the motivation for it. So all derived types from animal are guaranteed when we're using public visibility of inheritance to inherit the animal behaviors when the visibility of inheritance is public. So when we're looking at cats and parrots as animals, the question becomes, since any sort of derived type is, in this case, guaranteed to either inherit or redefine the members of the public interface of the base class type, is there some way that we could use the derived class's implementation of a behavior instead of the parents when we're looking at a derived object through the lens of the parents? So let me just go through what I mean. So whatever's in public here, and when we're creating derived types from animal using public visibility of inheritance, whatever, whoops, let's make sure it's in the right section. Whatever's in public is going to be available to all of those derived types. So in this case, cats and parrots. That means even if we do not define a speak function for the cat or the parrot, in that case, they'll inherit it because all of them are going to either inherit or implement this public interface. So it's guaranteed that all animals will be able to speak. So the question becomes, if they can all speak, is there a way to say that if I'm looking at Polly the parrot as an animal, could I use her definition of speak instead of the animal's definition of speak, provided that she has one defined for her? Likewise for Bubby. If I'm looking at Bubby as an animal, is there a way to use his version of speak instead of the animal's version of speak? Remember, to kind of revert back here is all these animals are guaranteed to have speak, whether it's inherited or whether it's redefined in the derived type. The problem here is that if we're looking at them through the lens of the base type's version of the functions being used, because we're just looking at that single outer scope. But is there a way to make the connection and go, okay, well, the cat implements the speak behavior. Instead of using animals speak, use the cat's version. And if one's not provided, use the generic version. So here we go on doing just that. So enter virtual functions. So the ability to define a function in a base class and have a function of the same name and return type in a derived class called when a user is interacting with the derived object through the lens of the base class. To do exactly what I just tried to point out is to declare that function as virtual. And what this says is that if you are viewing a derived object through the lens of the base class, so this case here, we're looking at Bubby as an animal or Polly as an animal. The virtual function says that if this behavior is called and the derived object has provided an implementation for it, use the derived objects version instead of the base classes. And to get this functionality, all we had to do is write virtual before the return type. This is a non-type attribute for this behavior. So notice here in cat, I did not do anything. So cat's declaration has stayed the same. Since animals speak is virtual, so would cats be? Should, maybe a kitten had inherited from cat. I don't know. I don't know on the example, but what I'm getting at is speak would be technically virtual here as well. Anyways, let's get to the bulk of this. So if the derived class provides a definition of a virtual function from the base class's interface, and again, it must use exactly the same name and type, return type. When we're looking at the derived object through the lens of the base class, so a reference to the base class portion of the derived object or a pointer of the base class type to the address of the derived class object, at runtime, the runtime system will use the derived class's definition of that function instead of the base classes. So what happens here? So just by tagging and saying, hey, compiler, speak in the base class, we're doing this in the base class, is a virtual function, the compiler knows that, okay, if a derived object, if an object of the derived type, such as a cat or a parrot, is being looked at as a through the lens of the base class, well, I should check and see if that type defines speak, and if it does, I'm going to use it in place of the base class's speak. So now if we were to create Bubby the cat, Polly the parrot, take a reference to Bubby as an animal, bound to Bubby, and then a pointer to an animal object, Polly as an animal, initialized with the address of Polly. If we ask either of those animals to speak now, the cat will say meow, and the parrot will say, Polly wants a cracker. So just trying to emphasize the utility of this. Let's say, I don't know, you're somewhere in your program, you need to maintain a collection of animals. So we've created some animal objects, and yeah, likely because we're taking pointers and stuff, maybe the cat and the parrot should reside on the free store, whatever. Right now, let's just show some of the utility of this. By having this virtual function, and let's say our program maintains a collection of animals, such as cats and parrots in this case, the cool thing here is that if I store the objects of those types in a vector of pointers to the base type, and then let's say I'm iterating through and visiting my animals and asking them to speak, they will speak according to their derived type, which is pretty powerful when you start thinking about the different things that you can use this for, and the different in the different contexts and applications that can arise from it. So what we've observed here is going to be kind of come to known as polymorphic behavior, and we'll get into a more concrete definition of that here in a moment.